Hey everyone, welcome back to physics. This is going to be lecture 22 of the course. And in this section, we're going to just take a quick aside, not really a little bit of an aside from our typical work, and just discuss high level some of the fundamental forces of nature. So let's jump into it. We'll call this section 4.5, the fundamental forces of nature. And as I say, this will be kind of quick, just an overview of what's to come and kind of to realign some of the things that we've discussed. So we've discussed several forces already. Just to list a few, we've discussed obviously weight, tension, like in a rope or a chain, friction. Good ones, normal force, right, etc. There's been a handful. So in our kinematics work and our application of Newton's laws of motion, these have all come up as typical examples, as well as others. There have been many. This may beg the question, how many different kinds of forces are there? How many different kinds of forces are there, in the universe? How many are there really? And it turns out that these are all examples of really two kinds of fundamental forces. And it turns out that two of the forces that we would consider fundamental are forces that we would obviously encounter in like kinematics problems, and then there are two others that are a little more they operate at smaller scales, and so they're not as relevant when we're talking about kinematics and when we're operating at the scale of the kinds of problems that we look at in kinematics. So it turns out there are four fundamental types of forces, right? And then two of those are things that we're familiar with already, and of which these are examples or kind of expressions of. And then two that we haven't really talked about yet at all, but we'll get into later. So the first one is gravitational interactions. And so we've seen lots of examples of this. Weight of a body. The weight of a body comes from our planet acting on the mass of the body. The weight of a body comes from our planet acting on the mass of the body. Right? So we know that W equals mg, the mass times the gravitational acceleration. And so we've seen that. Also, obviously, our sun holds Earth in orbit using this force. So anytime we discuss something falling or being in orbit, we're really just thinking of the gravitational force, gravity. Right? And then we'll study this force in great detail a little bit later, right? But that's really the first of the four fundamental forces. The second one, another one that we've discussed, is electromagnetic interactions. We haven't really talked about electricity yet or magnetism, but the forces we've looked at are fundamentally of this type. So electromagnetic interactions, right? And we'll get into this one in great detail in just 20 or 30 lectures or so. And so what are we talking about here? Well, we're talking about electricity, static electricity, magnetism, that type of stuff. I'm just kind of listing some things here. Terms you've heard that fall into this category. And so without going into the details of, like what is electricity, because that'll come in a future lecture, basically atoms contain positive and negative charges. Right, so atoms contain positive and negative charges, and from these imbalances can produce force between bodies. Right, it's a very simple way to put it, right? Not very sophisticated, but that's okay. We'll get into lots of detail later. But fundamentally, magnetic interactions all result from the fact that atoms contain this positive and negative charges, and they can be manipulated and juxtaposed in such a way that forces can be generated. So that's certainly the case when we see plus minus charges. We certainly think of electricity, but it's similar for magnetic forces. Magnetic forces, they may seem distinct, but they're actually the result of electric forces in motion. So magnetic forces are the result of electric forces in motion, right? And so hence we kind of lump magnetic and electric forces together, and really they're the same fundamental thing. Right, and we'll study these in great detail in a later lecture. Now, of the forces above that kind of could be thought to be examples of electromagnetic force or electromagnetic interactions, we're really talking about tension, friction, normal force, etc. Really, most of the other forces. So you've got gravity, which generates weight and things like that. But most of the other forces that we've discussed in kinematics are due to electromagnetic interactions. Okay. And so those are the two types of forces, fundamental forces that we're familiar with. Now, what are the other two? The other two are going to be forces that we're not familiar with in general. You may have heard the names potentially, but they're not going to be forces that you're overly familiar with, I would doubt, if you're taking Physics 101. So the first one, which will be the third fundamental force, is what's called the strong interaction. And this one is a little more intuitive, only because the description of it is a little bit more sensible. So this is the force really that holds the nucleus of an atom together. This is the force that holds the nucleus of an atom together. Now, if you think about your sort of your basic structure of the atom, right? You've got a nucleus, and inside that nucleus are protons and neutrons. So the protons are positively charged, and the neutrons, hence the name, are neutral. All right, this is sort of the basic description of it. So inside this nucleus, which is packed together very tightly, you've got a bunch of positive charge and a bunch of neutral charge. So you'd think the nucleus overall would have a positive charge, and these protons would actually repel one another, right? The protons, they're positively charged. They don't want to be butted up next to each other, but they are nonetheless. So the protons repel each other. They repel each other, and the strong force, that's what we're talking about here, is what overcomes this repulsion and holds the nucleus together. Right? So the strong force is very, very strong. These protons do not want to be next to each other, and yet they are, and they're very stable. Right, so this strong force is much stronger than the electromagnetic force. Hence, it is called the strong force. It has a very short range relative to the electromagnetic force, but inside its range, it is much, much, much stronger than the electric force. So the strong force has a very small range relative to the electromagnetic force, but inside its range it is much stronger than electric forces. Okay, and that would make sense, right? Because inside its range, it's holding all these protons together. So the protons are repelling one another based on this electric force, and the strong force easily overcomes that and holds them all together. So I don't know if this is the best way to think about it, but it's kind of like, it's a different force fundamentally than the electric force. It somehow binds all those protons together and holds them in place. It's outside of the electric force. It's different, much, much stronger. And sometimes this is called the nuclear force. Okay, and we'll get into this one in a lot of detail later as well, a little bit later. This is, when we get into more fundamental elements and fundamental particles, we'll definitely be talking about the strong interaction. But as of yet in the course, we haven't had any examples of the strong interaction showing up in our problem sets. When we're doing kinematics problems, the strong interaction just isn't relevant because of the scale. When we're talking about the scale of bowling balls and chains and motors hanging from walls and things like that, the strong interaction plays little or no part in that. Certainly no part that we would have to model. But once we move into the subatomic realm, the strong interaction becomes important. And so the last fundamental type of force is one that's very difficult to describe, so I'll just give you some bullet points on it. It's what's called the weak interaction. So you got like this strong force, and then you also have this weak interaction. Strong interaction, the weak interaction. Now, the weak interaction has really no direct role in our everyday world, but it is vitally important to the world of fundamental particles. So no role in our everyday macro, I'll say, world, but important in the subatomic and fundamental particle world. Right, so this is going to be way above our pay grade right now, but it's one of the things that the weak interaction is responsible for is it's a specific kind of radioactivity called beta decay. So specifically beta decay. So it's a kind of radioactivity the weak interaction is responsible for called beta decay. And you got to use your imagination. You can imagine that inside the world of the subatomic particles, there's a whole economy of activity. There's all kinds of stuff, interactions, exchanges, trade-offs, changes, blah, 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 all kinds of stuff happening. One of the kinds of things that's happening that's fundamental of importance is this beta decay. And basically, the weak interaction is the driver of this type of radioactivity. And what's really happening in beta decay is hard to describe at this stage in our development, but you can think of it as basically a neutron is transformed into a proton, an electron, and an antineutrino. So you start with a neutron, and it gives rise, and it's transformed through using the weak interaction, this beta decay, into a proton, neutron, and antineutrino. So you're probably thinking to yourself, like, what are we even talking about, right? Granted, I'm just giving you some bullet points on this. Think of it like this: it's of fundamental importance in the small, and it's not electromagnetism, and it's not the strong interaction. It's something different. It's one of the key pieces of work that it does is this radioactivity, is beta decay. Another thing, it's essential in processes that power the sun, right? It's in fission processes in particular. Now, where does the weak interaction fall in terms of its relative strength to the other three forces? It's much weaker than electromagnetism and the strong force. Weaker than electromag and strong force, but stronger than gravity at the subatomic scales. Okay, right. So you've got these four fundamental physical forces, right? You've got gravity, electromagnetism, strong nuclear force, and then the weak interaction. Right? These two they operate at the scales of everyday life. These two down here operate at subatomic scales. So everyday life, subatomic. Right? So hence we haven't really interacted much with forces that would be expressions of 3 and 4 yet. We've certainly seen lots of examples of 1 and 2 though. Okay, so again, this is just kind of a quick overview of this idea. We've had a lot of forces come into the picture, and this is more like a bucketing of them, right? So a lot of we just kind of think of these as the big buckets of the forces that we have so far encountered. We've seen a lot of this one, and we've seen a lot of this one. We will see a lot more of both of these as we progress in the course. We'll get into specifically electromagnetism for 8 or 10 sections, a lot of work there. We'll discuss, what electricity is, what all of this stuff is. And then we'll also dig in very deep into gravity and what's known about gravity. And then later, we'll dive into these strong and weak interactions. All right. So anyways, we'll leave it there. Again, just a quick section, and we will talk to you all in the next lecture. Take care.